I want to show two more aspects of the area between two curves. And so one of them is a tiny taste of the flexibility that integration has, which is that we can do things sideways. So here's the problem. We want the area between x equals 2y and x equals 14y minus 2y squared. That's a 14. And if you look at these are given as x in terms of y's. That's a hint that this is going to be a bit different from our usual kind of problem. Well, let's graph these guys. Well, let me graph this one first because it's a little harder, and that's going to set the scale. We'd like to get some axis intercepts. Certainly goes to the origin. X equals 0, y equals 0 works. What about the other y-intercept? That's where x equals 0. And I'm going to factor out a 2y. It's 2y times the quantity 7 minus y. So y equals 0 is one of the solutions, as we know, and then y equals 7 as well. So that tells us that y equals 7 is probably a good thing to plot up here. And it also tells us where the vertex of this parabola is. It's an x equals y squared form with a minus. So it's a parabola opening to the left. Its vertex is somewhere out here. And remember, the vertex is always halfway in between. The axis of symmetry is halfway in between the intercepts. So the axis of symmetry is here, or in other words, y equals 7 halves. Plug that in to get the x value. X is going to be 2 times 7 halves is 7. 7 minus 7 halves is 7 halves, or 49 over 2, or 24.5, or about 25. So let's see, 25, and just a tiny bit shy of that is the vertex. So here's that graph, roughly. And then, the x equals 2y, that's a straight line. That's pretty easy. So, for example, when y equals 7, x is going to be 14. So that's maybe a little more than a half. And so it's going like this. Oops, I kind of missed my mark there. Oh well. Okay. And so it's this area that we want in between. Now what I'm going to do is I'm going to put horizontal striping on that to suggest that what I want to do is, instead of taking the integral with like a dx, I want to take an integral with a dy. What I want to do is I want to think of this in terms of the quick and dirty version of the rectangle method. The area is going to be the sum of all the little bits of area. That's my notation for the little bit of area of an infinitesimal strip like this. And that's going to be the width, which we'll get more explicitly in a second, times the height of the thing. And the height's very small. The height is a little infinitesimal change in y, which we label dy. If you look in the book, they talk about Riemann sums and more careful versions of the rectangle method, where you start out with this as a delta y, and then you take the limit as that goes to 0. But unless you're doing something really finicky, this is a perfectly good way to derive an integral, to think of it already in sort of the infinitesimal case. And this is how it was done for hundreds of years, to be honest. That's how Newton would have done it. So what's the width? The width, we've got a number line here, basically, at a certain height y. And so for given whatever this height y is, the strip that we're analyzing, we just need to know how far these points are apart on that horizontal number line. And that's the difference between their x values. Oh, but we have formulas for those x values. If I'm on a strip of height y, then here's the x value of this guy, here's the x value of this guy. And so it's just going to be the integral, and I'm just going to say, let's say that's x sub r, the right-hand x, minus x sub l dy. And we can start putting in the limits. Ooh, we know the limits. Oh, wait, do we know this limit? Ooh, let's see. The strips start from y equals 0 and then end at an intersection. So that's still something we have to figure out. Let's see. Let me put it in here because it's a very similar calculation to this. Okay. Oh yeah, I shouldn't erase this though. So this was 14y minus 2y squared. Now this is the other thing. So one of the new things is we're going to get an integral with y being the variable. It's going to be a dy. It's not going to change the mechanics at all. It's just a new letter. But it's a different perspective of slicing things up horizontally, and it's important to be able to do that. And then the other new thing in this example is that we're going to have to do the intersection of these curves to find this mystery point. The intersection here was actually pretty obvious. They both went through the origin. But often you'll have to solve a system of equations to find the two intersection points that give you the natural boundaries of the region. These are not artificial boundaries anymore that were given to us. They're natural boundaries where the curves cross. Well, in this case, it's easy. We just set these guys equal because x equals x, and that's a plus 2y. So we get 2y is 14y minus 2y squared, or 0 is 12y minus 2y squared. Factor out the 2y again, and we get 6 minus y. Aha, well, y equals 0. That's the one we already knew about, and then y equals 6. So that tells us the biggest value of y, as we slice it up into these strips with different values of y, that stops at y equals 6. And then, as usual, I don't have a lot of room. Well, you can always go back to the picture. I hate to erase it, but that's what rewind is for. So the area, this integral, now I just have to put in, well, what was the right-hand value of r? That was the parabola value. That was the 14y minus 2y squared. And then subtracting the xl, the left-hand endpoint, was x equals 2y. And so instead of f of x and g of x, the version where you're looking at the area with a dx integral, these are these functions x of y, the two versions of x of y. This is up to get that better. Okay. That's not very visible. Okay. And now we can just do that integral. 0 to 6. 14y minus 2y is 12y. Not too shockingly, this quantity has already appeared. It's really the distance between the two. And we set that equal to 0 to find the 6 in the first place. That makes sense, because when the distance between the two curves goes to 0, let me just do the schematic again. When the distance between the two curves go to 0, that's exactly when the two curves intersect. And so that's going to be 6y squared minus 2/3 y cubed from 0 to 6, which is 6 cubed minus 2/3 times 6 cubed, and then minus 0 as it happens, because these guys die. And so that's 6 cubed times 1/3. I'm trying to avoid doing any hard calculations. That's 72. Okay. So this idea of being able to split up things, not just, as in the first video, vertically, and you get an integral of, let me summarize here. This version gives you an integral from left end point to right end point of top minus bottom dx. Here, we got an integral of the right-hand curve minus the left. That's so that it ends up being positive, dy. And now the points ended up being a top point and a bottom point. So even though I'm using the same word, right and right, like bottom and bottom, it's a rather different feel. The stuff in here are whole curves and functions. These are f of x and g of x. And the things in the endpoints are just the single number values, which usually got gotten by intersecting, or in this case, they were gotten just by given values that were in the problem.